Today we're going to be calibrating my 3D printer using computer vision and time synchronization for microsecond accurate measurements. Specifically, we're going to focus on figuring out how dimensionally accurate the motion system is. For now, this will mean verifying three things. First, if I ask any of my X, Y, or Z axes to move, say, 100 millimeters, I want to make sure they actually moved by close to 100 millimeters. Second, I want to make sure that all my axes are perpendicular to each other. And all of this only matters if we can move relative to our bed's surface, so finally we'll need to accurately locate the bed in 3D space. The goal by the end of this video will be to achieve sub 100 micrometer accuracy over the entire travel range for moving the toolhead. Since we have multiple microcontrollers on this printer, we'll also synchronize all their clocks within 1 microsecond of each other, which depending on how you measure it, is 10 to 100 times higher precision than what Clipper does. If you watched the last video, I'm still hard committed to not using Clipper, so we're going to be doing most of this from scratch, so buckle in. Anyway, in the last video we printed some of these calibration cubes. If we did everything right, they should ideally have each side 20 millimeters long with perfect right angles. We can at least verify the length of each side is correct with a pair of calipers. These are unfortunately not very useful for calibration since there are many similar shapes which our printer could have printed to produce these dimensions. A parallelogram like this is probably going to be the most likely result since it just implies that the axes aren't perpendicular but each axis is still linear. So this means that in some way we need to either directly or indirectly figure out how to measure the angle of the movements our printer is making. If you have a Core XY printer, you can visually see if you have some skew if you push the X rail all the way back and check if there is a gap on one side. There's also a third possible case that we printed something with non-linear edges like this. Since we're using fairly cheap rails for all the axes, there's a chance that they were slightly bent. All the ones I bought are from trusted suppliers, so they're probably fairly straight, but since they're still metal, if the printer heats up, they will inevitably bend a bit. For now, my printer isn't enclosed yet, so we're going to deal with this problem in a later video, though most of the methods as explained in this video will still apply. Another challenge of calibrating with printed objects that is worth mentioning is that when we initially print our shape, it's still going to be hot. And if you know a bit about physics, most materials like to shrink when they cool, so what you printed will end up being slightly smaller than what your motion system wanted. This tends to be fairly uniform, so probably won't affect skew detection, but will affect our ability to verify the steps per millimeter scaling factor of each axis independently of the type of filament we are using. To try to measure the skew, firmwares like Clipper recommend printing specially designed shapes like these that have more distances you can measure, which will change if printed with skew. There's a bunch of different shapes you can use to do this calibration. Probably the most popular one I've seen advertised on YouTube is this cauliflower model. If you use a printed calibration model for calibrating, the pros are that you don't need any special equipment to do the measurements aside from some calipers. It's also fairly quick to perform and very simple in terms of things that can go wrong. The cons are that you need to print something, so the results will vary depending on your filament's quality and shrinkage factors. You also may need to print multiple patterns to characterize skew between all pairs of axes, individual axis scaling, and nonlinear skew. To achieve very good results with this method, it's also dependent on your skill with calipers to measure the shape perfectly without squishing it. The second group of solutions you'll see are the computer vision based ones. You'll see this a lot in Bamboo Labs printers. The general idea is that you have some camera rigidly mounted to the toolhead. Then as the toolhead moves, it will look at some well-defined patterns to measure the behavior of the movements. Bamboo also sells this larger calibration board that you can put over your entire bed to perform more comprehensive calibration. Most likely Bamboo Labs and other printer manufacturers are using something like this in their factories to do the initial calibration of pre-built printers before you buy them. If you're using Clipper, there's also an open source version of this on GitHub. In general, this is a fairly classical problem in computer vision. My really old laser cutter even comes with a camera and a calibration sheet that you can use to do automated alignment. If you use a camera-based solution, the pros are that you don't need to print anything, so the results are completely independent of your filament type. Also, this approach can simultaneously measure linear and nonlinear skew and scaling in all axes. Since you'll be automatically collecting hundreds of measurement points, it also has the potential to be more accurate than other approaches. The main con is that you need specialized equipment like a camera and a high-quality calibration board to perform the whole process. Also, if you don't already have the software to do it, you'll need to set up a full computer vision pipeline to do this process. Anyway, I'm a sucker for computer vision, so we're going with a camera-based solution. First, we're going to build a temporary test setup that looks like this and consists of a downward-facing camera and a calibration board. All of the precision in this setup is going to come from this Truarco calibration pattern that looks like this. The most important property of this board is that it has points that are really easy for a computer to detect in the image. And these points are known to be precisely located in space. More specifically, each square is 5 by 5 millimeters. Also, the board is extremely flat, so we know that the z-coordinate of all the points is the same. To make one of these boards, I first found a script to generate a PDF for the pattern off the internet, and then we can put it out on a regular 2D printer at 100% scale with no margins. Now unfortunately I have the cheapest laser printer off Amazon, so if you try measuring the sides of the pattern with a ruler, you'll find that it isn't close to being dimensionally accurate. The simple fix to this is you can just measure the X and Y sizes with a ruler and then scale the PDF to correct for any error and then reprint the sheet. Then we get a fairly precise pattern, which is less than half a millimeter out of spec according to my ruler. Over the entire range, that's around 0.1% error. Note that if you have an inkjet printer, you'll probably get slightly better results as there is less heating of the paper involved. The second problem you've probably noticed is that the paper isn't flat. To fix this, I'm going to be attaching the paper to this cheap glass picture frame. In general, most glass you'll get will tend to be extremely flat due to the process by which it is made. Anyway, first I'll cut a frame-sized sheet out of the paper. Then, since I'm using thick cardstock paper, I can spray the back of the paper with spray adhesive without too much of it soaking into the other side. Note that you want to wait 30 seconds after spraying the adhesive before attaching the paper to the glass. Then we can press the paper onto the glass frame. Finally, since I did a terrible job of aligning the paper, I'm using a knife to clean up the edges. Note that if you're really serious about precision, you can also buy pre-made patterns from some companies. The cheaper $100 ones are going to be slightly better quality than the DIY one I just made, though there are also crazy expensive ceramic ones you can get. Not enough of you people have subscribed to my channel yet for me to buy one of these, so I'm going to be sticking with the DIY one for now. The second part of the setup that we need is a camera mounted to our tool head. I made this 3D printed adapter in which we can attach a 4K 3DO nozzle or enclosure camera with some screws and spacers. Then this screws onto the tool head in place of the existing screws. Note that for this to work well, the camera has to be rigidly coupled to the tool head, so all the screws need to be tight and the wire needs to be properly strain relieved so it doesn't pull on the camera. Lastly, with the board placed on our bed, we need to focus the camera at around half of the Z travel distance. You can find these 3D printable tools on the internet that will allow changing the focus by turning the lens. Note that if you have the glued 3DO nozzle camera, you need to heat up the camera to around 100 degrees Celsius and then turn the lens to break the glue that locks the focus. What I haven't explained yet is how we're actually going to use this to calibrate our printer. So far what we've done is we've mounted a camera on the tool head and we placed the calibration pattern we made on the bed. Generally you can think of a camera as having an image or a sensor plane in which your image pixels live. When we take a picture, rays of light will go from our calibration pattern and converge at the optical center of our camera. In turn, we'll be able to see the corners of the pattern as pixels in our image, which are the red dots on screen now. At this point, we have a bunch of triangles like these two that are being highlighted. Since we are looking at a well-defined pattern with 5mm spacing between corners, we know the XY coordinates of the bottom side of this bigger triangle. Also, if we can find the corners in the image, we can get the pixel coordinates of the corners in order to get the length of the smaller triangle. Assuming we also somehow know the focal length of our camera, we can use these measurements in some high school trigonometry to calculate the coordinates of the center point of our camera. Know that the focal length is something you can actually figure out at the same time after taking many pictures of the calibration pattern. This process is known as bundle adjustment for anyone who wants to read up more on that. Anyway, the result of this process is that we will know the 3D position of our camera in space. Going forward, I'll just call this the real position. We also know the machine position of our 3D printer since we can ask the 3D printer to move to a specific point in space after we homed it. These 2 points won't be perfectly aligned since our camera isn't perfectly aligned with our nozzle. What we'll do next is repeat this process by moving our tool head in a grid pattern and measure the real position with our camera at each machine position. At the end, we'll have a huge list of points representing where the machine thinks it is and where it actually is in space. What you see in this picture is what it would look like if there was no skew. If there was skew, then most likely you'd see something like this. We're going to assume for now that all the skew is linear, so we can put all these values into a matrix equation that looks like this. Basically, if you have some real point in space, if we multiply it by some unknown transformation matrix T, we can find the corresponding position that our machine needs to go to in order to reach that position. Assuming we know the value of T, then when we are printing, we're going to be plugging in all the points from our G-code into this equation before we give them to the printer. For just 1 point, the elements of the matrices look like this. In order to find the value of T, we're going to be populating the matrices with all the hundreds of points we collected during the camera grid scanning phase. If you've taken a linear algebra course in the past, then you'll probably know that we can solve for the transformation matrix by multiplying both sides by the inverse of the real positions matrix. Anyway, let's start by doing the grid scan for real. In round 1 of scanning, I'm fixing the bed in one place by taping it to the bed and moving the machine in different X and Y positions. Some people might have noticed that we never verified that our calibration pattern isn't skewed since we never measured that. Well, it actually doesn't matter, since in round 2 of scanning, we'll do the same thing but with the pattern flipped 180 degrees. Any measurements we get in this round should have an opposite skew compared to the first round. When we do the math at the end, we'll do some rotational averaging of these 2 skew matrices from these 2 first rounds to cancel out the skew of the calibration pattern. After these 2 rounds, we'll do another 4 rounds of measurements with the board tilted at different angles. I'm not taping the board to the bed in these rounds since the rigidity doesn't matter for these and we'll only be using this data for calibrating the camera's focal lengths. If you already know the focal length of your camera, you can basically skip these rounds. After you do all this, the camera and machine positions you'll get will look like this. Currently, the transformation matrix between the 2 point clouds has a lot of big scary numbers in it. As is, we can't use this since we obviously don't want to have a big jump in position when we apply skew correction. The current issue is caused by the fact that our camera and machine don't see in the same coordinate system. I could have arbitrarily shifted, rotated, or tilted this board when taping it to the bed, so we can't trust any rotational or translational components in our matrix. Note that this also means that we can't use any of this data to determine how level our bed is. Mathematically, if this is our starting matrix, we can get rid of the rotation and translation as follows. The translation is easy to get rid of since we just need to set these terms to 0. The rotation is a bit more complicated. Since this isn't a math video, I'm just going to tell you the answer is that you need to perform an RQ decomposition of this matrix and take the R matrix as your new transformation matrix. If you get rid of all the rotation and translation components in the measured camera points, then the two sets of points will look like this. They're basically identical now aside from very tiny variations due to the skew of the machine. The final transformation matrix that we will use for skew correction will look like this. What these close to 1 diagonal entries mean is that our steps per millimeter values for all our motors are fairly accurate. These other values are the skews between the axes. If we had no skew, these would be 0. If you try multiplying some points by this matrix, you'll find that they will shift by roughly 0.2 millimeters per 100 millimeters of travel, so our printer is actually pretty well built as is. At this point, we have aligned all of our axes with each other, but we still haven't aligned the bed with our movement axes. Best case is that the bed is completely flat and centered at the origin, so we can just lay down plastic without issues. But more likely the bed might not be flat, so if we try printing on it, the filament might not stick well to the bed. Even worse, the bed could be crooked relative to our movement axes, which will make it even harder to lay down filament. If you've seen other printers, you'll know that the gold standard in this area is to touch or scan the bed at different points with the toolhead to determine the position of the bed in space. As I showed in a previous video, I have a PZ probe which allows us to measure when we hit the bed, so we're going to be using that to develop a bed leveling procedure for my printer. But the first problem with this is the plastic is really annoying and loves to stick to the nozzle. This means that if we probe the bed, it'll be offset by however thick the plastic layer is compared to a clean nozzle. Usually I just use a brush like this to manually clean it up before each print, but I don't want to do this every time. Some printers like my Prusa XL have this fancy procedure that does some test probes to try to get the plastic to come off the nozzle and stick to the bed before taking a measurement. With harder materials, I've seen this fail a few times, so I still want to have a physical wiper for my Voron Zero. I did some searching on the internet and I really like the idea behind some of these Voron Zero wiper mods, which allow the wiper to be stowed away when not in use and can slide below the nozzle with the servo motor when needed. Unfortunately, I already have most of the space back there occupied by this air filter, which will get its own dedicated video in the future. So instead I ended up designing a custom wiper mod that takes up less space. Starting with the servo, I'm going to be clipping off these side mounting brackets and sanding them down flat to the body. On top of the servo, I attached this press fit horn that will attach to a silicon wiper from a Bamboo Labs printer. Then to attach it to the printer, I have this bracket that mounts to the railing. We can then temporarily remove the air filter and slide the servo in from below. On top of the servo goes this clamping plate, and then the wire goes down the railing. We then need to verify the height of the servo relative to the nozzle, and once we think it is good, we can tighten the clamping plate to lock the servo in place. I also already extended the stock wires on the servo so they can go into this connector on the main control board we made in their last video. Anyway, a few macros later and here it is in action. Obviously, if you've ever used one of these, you'll still often have plastic oozing out even after you clean the nozzle. The probing still works if the nozzle is slightly dirty since most of the plastic will be melted and will compress before the probe is triggered, but it does leave a mess on the bed. The other problem with my tapping approach is this toolboard. If you think about it, the life of a tap is pretty crazy. First, the pi will tell the mainboard to start moving the z-axis up. Then when the PZ probe is tapped, it will be picked up by the ADC of the toolhead within 120 microseconds. Note that since I originally talked about the PZ probe software, I updated it to sample the sensor roughly 8,000 times per second. If I spent some more time tuning it, I could probably get this up to the full 200,000 times per second that my microcontroller supports. Anyway, then the toolhead needs to send the signal back to the Raspberry Pi. I measured that currently round trips over USB take around 200 to 400 microseconds. So in one direction, this is around 150 microseconds plus or minus 50 microseconds. Then after the Pi has done some processing, it needs to send this data to the mainboard, which will finally stop the motor. If the motor is currently in the middle of a step, it will also take some time for that step to complete. Finally, the Pi will read the last step position that the motor reached and use that as the probed offset of the bed. Rounding things a bit, it should take less than 500 microseconds to stop the motor. This entire time, the Z motor has still been moving, so we'll overshoot the zero position. At a probing rate of 10 millimeters per second, the motor will travel by around 5 micrometers extra beyond the zero position. This will also vary by a few micrometers depending on the jitter of the USB connection and how long it takes for the Raspberry Pi to process the hit. Note that if you're using a slower connection like serial or CAN for your toolhead, this would be way worse. Also keep in mind that the problem is only this severe if we use a separate toolhead board. If our probe was directly connected to the main control board, then it would be able to directly stop the motor without extra hops. On this channel, we don't settle for 5 micrometers of precision. We're going to push the error down further while keeping 2 separate microcontrollers by improving upon one of the tricks that Clipper uses to improve end-stop accuracy. The first thing you should remember is that when we tell the main board to move the X motor, we are telling it the exact time at which we want it to start moving and the exact speed at which we want it to move. When the toolhead sees a tap, it'll instantly record the time on its local clock at which the event happened. And when I say instantly, I mean that this can be wired up to have 0 CPU involvement, so it's mostly dependent on the clock resolution, which is less than half a microsecond. Then when the toolhead sends the signal back to the Pi, it'll include this time. The Pi will store a list of all the previous motions it has sent to the main control board. This will look like a table where at every point in time, we know the position all the motors should be at. So in theory, we could look up in the table the exact step at which the Z motor was at when the probe was triggered and use this as our probed Z offset. This should allow us to get less than 1 microsecond of error, excluding the ADC sampling time and the time synchronization error. There may also be some error if the motor driver isn't moving the motor at the right speed, but the hope is that that will be negligible. Unfortunately, now we have a new problem, which is time synchronization. The Pi, the main board, and the tool board will all have separately running clocks, which at any given point in time will have different values. They're also all going to be running at different rates. As an example, let's suppose our Pi's clock is increasing by 1 second every second as shown by this line. The other 2 clocks would be increasing at some other rate per second with some offset based on when the microcontrollers were turned on. So ideally, we need to figure out the equations of all of these lines such that at any point in time, we can figure out what time on one clock corresponds to on all the other clocks. We also need to constantly recalculate this since as the microcontrollers heat up and cool down, this will also change the rate at which they count time. How Clipper solves this is basically by periodically sending requests to each microcontroller to ask it what the current time is. First, the Pi will record its initial time, and then it'll send a request to one of the microcontrollers. Once the microcontroller receives the request, it will respond with its current time. Then once the Pi gets the response back, it will record the local time at which it received the response. And of course, it'll also receive the time it received from the microcontroller, which we will call the remote time. The Pi can then estimate that the time it got from the microcontroller is roughly equal to halfway between when it sent and received the request, plus whatever the current offset is between the 2 clocks. If we assume that the clocks all move at the same rate, we can just solve for the offset value now and use that for converting between times on our Pi and our microcontrollers. But since that isn't the case, we'll collect multiple points every second that look something like this. The USB bus is usually busy sending other packets, so the points will also include a few hundred microseconds of noise. From these points, you can fit a line that best fits our data, and then use that line for any clock conversions you need in the future. Given that the round trip time is a few hundred microseconds, the error with this approach will probably be around 100 microseconds or less. If you do assume the USB round trip time is roughly symmetrical and do some of the other tricks that Clipper performs, like only using the minimum round trip type for offset estimation, there's a high chance that the error is actually probably less than 10 microseconds. But we can still do better than this. The important insight that we need in order to improve this is that we don't actually care about the Raspberry Pi's clock being in sync with the microcontrollers. All we care about is that all the microcontrollers are perfectly in sync with each other since they are doing all the motions and sensor readings in their own clocks. A lesser known feature of USB 2.0 is that every 1 millisecond it will send out a startup frame packet to every single device attached to the same USB controller simultaneously. By simultaneously, I mean the only error should be the speed of electrons flowing through the wires, which should be negligible. So we will have each microcontroller record its local time value at the time it received the start of the frame packet and asynchronously give these to the Raspberry Pi. On my microcontrollers, I can do the recording without CPU intervention, so with less than half a microsecond of error. Now at the start of each USB frame, we have one time value from each microcontroller, and we know that all these time values are recorded at basically the same time. This means that if we ever get a time from one microcontroller, for example with the time of our probe, we can convert it to a time on another microcontroller, for example the one running the motors, with an equation that looks like this. In practice, we would still do linear regression using these points, but the result would be a differential scaling factor between the 2 microcontrollers. Once you do that, you can be fairly confident that you have less than 1 microsecond of differential clock sync error between all your microcontrollers. Anyway, to see if this makes a difference, I had the printer probe the bed at the same point 100 times in order to evaluate how much noise we have in our measurements. The blue line is the step position at which the motor stopped after each probe. The red line is the position we predicted the probe was hit at using the timing data and sub-step interpolation. The gap between these 2 lines is the amount of distance our bed traveled after the bed was hit but before the motor was stopped. And if we compute the standard deviation of each of these lines, you'll see the timing-based approach is about twice as consistent as the regular approach in this setup. I'm guessing that most of the error now is from the ADC sample rate being too slow. I did quickly try boosting the sample rate, but then I found that the values also slowly drift over time, so I'm guessing that my machine isn't actually rigid enough to achieve more accurate probes. The last thing I should mention is that even if your probe is directly wired to your main control board, timing is still important if your extruder is on a separate microcontroller. If the timing is off, then you may see cases where your layers aren't aligned with each other, since the extruder and XY motors may start and stop moving at slightly different times. This will be much more noticeable than the probing error, since we are going to be going much faster in the XY directions. At this point, we can finally do our grid probing to probe the height of the entire bed. For now, I'm doing a dense 8x8 grid just to get lots of data, but I'll probably reduce this or just probe the printed region later on. If you plot all the points, you'll get something that looks like this. Overall deviation is 0.7mm right now. That's probably because this is from before I improved the noise filtering, so there is one outlier point. Also, you can see that the board is slightly slanted. We can do some math and fit a best fit plane to this data. Relative to this plane, the deviation is only 0.3mm. Now we have two options for how to correct this. The first one is, since we have a best fit plane, we can just rotate the whole bed in 3D space and just print it on that plane. Doing this too aggressively has some downsides, so I'm going to first try to physically level the bed a bit. On the Voron 0, we know the positions of the 3 screws holding the bed in place, so we can find these XY values on our bed plane to estimate how much each point needs to move up or down. In my case, the biggest issue is that I need to raise the front screw point a bit. Now comes the most janky part of this video. I didn't include any leveling screws in the bed, but I do have these tiny 0.4mm washers, so I'm just going to insert one of these below the front screw. Then after we reprobe our bed, the results are much better with only 0.2mm of axis aligned deviation and 0.1mm aligned with the best fit plane. Now the last problem we need to solve is that our bed still has high and low points. Ideally, we want to print following these curves to best stick to the bed. The most obvious algorithm for this is to just shift every point consistently up or down based on the Z offset at that point, but this will result in your top surface not being flat. Instead, what most firmwares allow you to do is to use Z fade leveling. My understanding is that Marlin has this enabled by default, while in Clipper you need to explicitly enable it. Basically what this will do is perfectly follow the bed curves close to the bed and gradually reduce the offsetting as you go up. This effectively is squishing your lower layers to make your higher layers flat. Note that if your bed is not level overall and you try printing, one side of your print will be squished while the other side is elongated, so the bottom surface of your print will be crooked. This is why even if you are using probing to measure your bed, you generally still need your bed to be relatively flat relative to your XY axes. Anyway, let's actually print some stuff to steady check that I'm not going crazy. First, I printed this flat sheet to verify the bed is well leveled. There is still a bit of over-extrusion that I'll need to adjust later, but in the end this turns out fairly well. And here's the PO you've all been waiting for. Then I printed the Clipper recommended XY Skew calibration object with and without skew compensation. This ended up being more annoying than I expected, since I ran into a lot of trouble with layer shifts caused by the build plate shifting. So I ended up enabling brims for all of these prints to stop delaying this video. Hopefully this issue will be resolved once we better tune the extrusion parameters. Anyway, here are the XY skew object results compared to the ideal shape. We were able to get rid of the skew since the diagonals are now the same length. The scaling is now a bit off though, probably because the calibration pattern is not perfect, but that should be a pretty easy fix, since we just need to make the diagonal entries of our skew matrix 1s if we want to ignore the calibration pattern scale judgment. And lastly, let's do a benchy just for fun. There's still a lot of stringing since none of the retraction and extrusion settings are tuned yet, but I think a lot of the details came out pretty well, and the bottom text is better than most printers I've owned. Okay, that's all for this video. For now, we've skipped testing the effects of thermal expansion on the bed, rail, and nozzle offsets, since there will be another video later dedicated to enclosure calibration and thermal compensation. The next video will probably be about going fast. Bye!